All right, thanks, Tony. Thanks, everybody, for coming today. And I want to introduce our speaker, Andrew McCallum. So Andrew got his PhD at Rochester from Dana Ballard, working with Dana Ballard, and then spent some time in Pittsburgh, various forms, was a postdoc there, and then worked at a company there. It's pretty mental. And went straight to UMass.
Yep.
He's been at UMass for a number of years. And he's well known for a bunch of things in the field. I think what I associate most with him are a couple of things. One is he's done great work on kind of information extraction, natural language processing, dealing with really messy data like that, and making a lot of progress in that area. That's what we're going to be talking about today. And also on the kind of more machine learning and algorithmic end of things, he's done a lot of work on structured prediction problems. Where you have complicated outputs in your with relationships between different things in the outputs and your learning models in that kind of space. And he did the original paper on conditional random fields. That was in 2001 with Lafferty and Pereira, and I just found out that won the test of time from ICML. As papers that last 10 years later get voted as the papers that have had a significant impact in the field. And also, Andrew's done a lot of work separately on toolkits and things like Mallet is a popular tool program that people use for natural language processing, and more recently, Open Review. So he's developed this Open Review system that some of you may be familiar with from iClear recently, submitting to iClear. So Open Review is dealing with the reviewing for that, and there's many interesting plans for iClear, for Open Review, like linking it up with archive and things. So feel free to talk to Andrew afterwards about some of that stuff. In any case, I look forward to his talk, and here's Andrew.
All right. Thanks. It's great to be here at Toronto. So I'm giving a talk today. I'm giving another talk tomorrow that will be, actually, the two talks match actually the dichotomy that Rich just talked about. This will be about natural language processing, a bit more application-oriented. The talk tomorrow will have much more novel machine learning content. The other thing I want to say is I want to encourage you to interrupt me to ask questions during the talk. I'd be really happy to turn this into a dialogue. And thank you for the first one. Go ahead.
Where's the talk tomorrow?
Okay, yeah, I actually don't know myself. All right, so many companies which in their youth focused on web page search are, now that we're spending much more time in front of smaller screens, thinking much more instead about dialogue systems, about question answering, about knowledge bases, about a much more structured view of the world so that questions can be answered in a much more succinct fashion. Things like Freebase and these knowledge panels that you see off to the side are another example of this. And this consists of an entity and a number of relations to other entities, where the relation types are these bold terms here, and those types came from the Freebase human designers who decided what relation types would be in the system. And there are a lot of them, and they worked hard to create a large type system, but there's never really enough. And we can see evidence for this from multiple corners. But one is, even just in web search, it's well known that the majority of the mass of web queries are in the long tail of the more esoteric things that people ask about. So, for example, if we wanted to know who did Jeff Bezos criticize, Freebase has no answer for us because it has no criticize relation. And somebody who stays studying political science and various sad election outcomes and things like this, might like to do a study of these kinds of relations. So this talk, so what we'd like to be able to do is to have a knowledge base of entities and relations with an open schema that lets us ask about anything, the same way we can ask about anything when we issue a keyword-based web query, but at the same time has an entity-relation structure about which we can reason, and handles those two things together. And that's what this talk is going to be about. So we're talking about going from text to some knowledge base and then doing reasoning on top of that knowledge base. And let me get started briefly by just giving you a few examples of some knowledge bases that I've been building in the past. One of them I did all the way when I was back at Carnegie Mellon you can get the sense of the age of the project by looking at the browser on the right-hand side. That was 10 years before Google Scholar launched. It was a system that spidered the web for computer science research papers, extracted the text, used cutting-edge information extraction methods to get the title of the author, etc. They were hidden Markov models at the time, and put them into a searchable system. And at UMass later, about 5-6 years later, we built a more modern system that was using conditional random fields and knew about a lot more object types and the relations among them. And now we're working on building a knowledge base of all scientists in the world by extracting and integrating information from papers and patents and even tweets and blogs. And we're also very interested and have been working in building a knowledge base of the scientific content inside the body of those papers as well, scientific entities like materials, equipments, organisms, processes, tasks, and methods of understanding the relationships between all of these. And why? Because we're trying to accelerate the progress of science, and you can imagine how these various things would help. As Rich mentioned, also as an aside, we're very interested in trying to revolutionize the process of peer review by building tools that help support open peer review, or at least support experimentation in the way that reviewing is handled. And so with that in mind, we've been working on web systems for supporting peer review for iClear and a number of other conferences. Looks like we're going to be supporting UAI this coming year. We're already in discussions with CVPR and ICML for the future as well. I'd be happy to talk with people about that afterwards as well. Okay, but back on track. Here, let's talk briefly about what this process looks like generically, and I'll give you a super brief tour just touching on a disparate array of some things that we've done, and then we'll get into the core technical piece that I want to tell you about. So we start with some text. From this, we'll extract some entity mentions, spans of text where we're mentioning names of people or organizations or other things like this. And then we want to extract relations from those, like Wei Li is affiliated with Tsinghua University. And then because Wei Li might be mentioned more than once, and also because she might be mentioned in some structured data that we also have, we want to resolve these all together so that we find the multiple places where Wei Li is found. And then we think about this as the truth about entities and relations that we can inject into some knowledge base about which we can answer questions. But the information extraction components aren't perfect. They do make mistakes, and the errors tend to snowball through this pipeline. And so I and others have been interested then in reasoning with uncertainty about this pipeline, passing forward multiple hypotheses, having top-down information help resolve the ambiguities in the raw text. And think of this as joint inference. And there are many examples of this, most of them having to do with joint inference about information that falls within one sentence or maybe within one document, because it's easier to manage the kind of dependency structures that are there, and it's just less data about which to reason jointly. But I think there's actually much more juice toward the end of this pipeline, because that's where more data is getting aggregated together. There's more opportunity for that kind of jointness. And when we think about this all together, it gives rise to all sorts of juicy research issues, like, well, how should we represent and inject uncertainty from extraction into the knowledge base? Or how can we use knowledge base contents to help information extraction, kind of top-down reasoning? And then lastly, something that in a way seems like engineering, but actually I find very interesting, which is that extraction isn't one shot. It's not like I'm going to be given my 10 million documents today and then run extraction on them, try to do it jointly, and then I'm done. No, I'm going to get another 10,000 documents tomorrow, and some of the evidence that I receive in those documents often should cause me to change my mind about some of the interpretation conclusions that I came to on data that I saw yesterday. And I'd like to be able to revisit those old decisions without reprocessing all that data from scratch. So in some sense, I would like to use this knowledge base infrastructure not just to store the final result of truth discovery, but to help me manage the extraction process itself and make it easier to go back and revisit these conclusions. So with that in mind, we have been enlarging the purview. Yes, thank you. I do, actually. And maybe I didn't put a P in front of the KB, but maybe I should have to reflect what we actually care about. Well, I guess I don't want to store in the knowledge base just the final entities and relations, because there might be some things that even aren't necessarily shown here, like just the results of parsing that may have some uncertainties that I want to make it easier to revisit as well. So with this in mind, we've been enlarging the purview of the knowledge base to store not just the final results, but also to store all these intermediate results, making it easier to go back and revisit them in targeted fashion. And one way you could say, well, you've just sort of rearranged the boundaries on your boxes and arrows diagram, and what does this mean really? And that it's a justified comment. But we find that this worldview just helps us think about new solutions to certain kinds of problems in ways that come naturally with this worldview that weren't coming so naturally before. And let me give you a quick whirlwind of just a few of those before we focus in on relation extraction. So before we get there, let me say, so it was previously the case that truth discovery happened outside the database, and then we inject our estimate of the truth in there. Now the only thing that comes into the database is the raw evidence. And truth discovery happens inside the database. And this reminds me of epistemological philosophy, which says you don't get to observe the truth, right? You just observe the evidence, and it's up to your own internal reasoning to discover what the truth is. And so we've taken to calling these things epistemological knowledge bases. So the only thing you're allowed to inject is the original raw evidence. And that applies to other things that we might like to inject into a knowledge base, and that includes things like human edits. And when you build a knowledge base, invariably, whether it's built by machine or by humans, it's going to have errors in it, or it's going to be out of date. The people using the knowledge bases may be incented to provide corrections, and we want to be able to handle them. The classic way to handle corrections is like Wikipedia does, right? The human editor erases the old value of the truth, writes in a new value, and maybe you keep some provenance edit history so you can unroll it if you like. But that's really unsatisfying. You know, there can be edit wars, or a human might make a correct edit, but then 6 months later the state of the world might change. The human doesn't notice, but the machine notices. We'd like the machine to be able to overwrite what the human said sometimes. And so with this in mind, we treat human edits not as an erasure of the truth, but as an additional kind of evidence. Like it's a mini document that says on this date, Rich said that this thing was true, and that evidence can sit beside evidence from elsewhere, and we'll reason about it all together to decide how much we trust Rich versus other sources, etc. And we can jointly reason about this truth discovery and people's reliability. Yeah. Okay. So that's one quick example. So another is never-ending inference rather than running extraction, and then all the KB entries are locked in. You can think of inference as constantly bubbling in the background, and with more evidence, with more time, with more computation power, we'll do a better job of discovering the truth, always reconsidering them. Another area in which we've done work is in entity resolution, and not just co-reference of entities, of mentions into entities, but also of ontologies and schemas and relations and values. And by the way, it helps to do all of these together jointly. This is especially important when the only thing you're allowed to inject is raw evidence. So entity resolution needs to be done even before you can understand where your incoming data belongs. And we've also been doing work on resource-bounded information gathering, where, say, there are some holes in our knowledge base, places where we know some information is missing. We've been able to fill that by looking on the web, but we can't process the whole web, so we're going to try to make some targeted queries, explore the web in targeted fashion to try to guide us efficiently to exactly those pages where we think we could find information that would help us fill in the database, and we've been using reinforcement learning for that. And then lastly, if we're going to do this at large scale, we need to think with parallelism in mind, and Samir Singh, my student, did a thesis on trying to reason about probabilistic inference and parallel distributed processing in very tightly intertwined fashion in ways that provided multiple orders of magnitude gains over more black box methods like MapReduce that don't think very carefully about inference and parallelism together. Samir is just a starting faculty member at UC Irvine, actually, just this fall. Okay, so now I want to zoom in and focus on relation extraction. And this is what the rest of the talk will be about. Yes, in the back. Hey, Nick.
Can you go back to the previous slide?
Yeah.
Maybe I'll talk about it later, and then we can just punt it. But what's the idea of a text document? If you had that.
What's the idea? What? Sorry.
I'm trying to understand understand the human edit. If I make that edit, it's a very small document. If I add that document in 100 times, is now the system much more sure that it's true?
Right.
What's the model of the document?
Right, right. So that will be up to the inference procedure, and maybe that inference procedure, as you're pointing out, should capture the notion that multiple repetitions from the same person should not count as independent evidence. Yeah, so there are a lot of open questions about how best to do this kind of inference. A big one that we've been struggling with is how these edits interact with entity resolution, right? Let's say that I'm seeing an entry for Fernando Pereira, and it says that he's at UPenn, but now I know that he's now at Google, and so I enter an edit saying, well, this Fernando Pereira is at Google. Then I realize that my previous notion of Fernando Pereira was actually confounding two people. It's actually true. There are two Fernando Pereiras about the same age, both computer scientists, both actively publishing. The non-NLP one publishes an MPEG compression. And so now this entity gets split, and where does the edit go? Or maybe I'm saying, like, Fernando's not at AT&T, he's here, but then when the record gets changed to show that he's at Google, my edit saying Fernando at AT&T doesn't get resolved against the Fernando at Google anymore, because so we've been thinking about edits. Have a notion of, we've been calling them packaging and payload. There's like some information that sits on the outside of the edit that tries to make sure it gets resolved into the right place, and then the payload of the inside. This is like the edit information that's going to cause some change, but it should not. Yeah. Anyway, there are a lot of really rich, fascinating issues here that I think we have yet to resolve, and this is the thesis topic of one of my current students. All right. You're doing great with questions, by the way. Keep them coming. Okay. So let's talk about relation extraction and how it's done traditionally. So usually it's a supervised machine learning task. The human designs by hand some schema of relation types that we're going to care about. We go to find some data. The human labels this data according to those types. And then we build some machine learning model, which we hope on some test data will make some accurate predictions and produce the right relations in the end. Labeling this data is a huge pain. I mean, labeling data is always a pain, but it's an extra pain for tasks like this. There's just a lot of moving parts to a relation, and human labeler agreement on relation extraction is often not high just because it's such a fiddly task. Another task that avoids much human labeling is distant supervision, in which we rely on being given some database that already has a schema that we care about, that's already filled with a lot of data, for which we also happen to have a lot of text with overlapping information. The text isn't labeled, but what we can do is try to find places where records from the database have been, quote, rendered in unstructured text, and align them with each other. The alignment effectively labels the unlabeled text, then we treat that as if it were labeled truth to train some machine learning extractor on which we can run on new text in order to find more facts to fill the database. This works pretty well. This has been a broad family of methods that have done the best over the past several years at the NIST Text Analysis Conference Knowledge-Based Population Competition. Yeah.
And is this based on a dictionary, or is all of these things are related, so you can figure out that when you begin studying math, there's some natural language processing has to work?
Yeah, that's right. So often the way these things work is it finds this entity pair. It finds any sentence in which the entity pair occurs in the text, and then assumes, and this is a problem, that text is expressing the relation that we had here. So if it says, Obama went on vacation to Hawaii, and the knowledge base says Obama was born in Hawaii, then we're going to think went on vacation is a textual expression that means born in. And so that's obviously a problem. Historically, in the relation extraction community, for some reason, many of the examples that people often build for their talks have to do with Obama. And my research group just yesterday resolved that we're going to continue to have Obama examples for the next 4 years. Okay, so that's one problem. Another problem is that, again, to build on this, you could start to do some tail chasing, right? like you get that vacation born in confusion wrong, and then you start to extract with that, and then you start to fill more examples here, which then just causes even worse problems. And now so another possibility is just to be completely unsupervised, just to have no schema at all. What do I mean by this? This is the approach taken by Ornazioni at University of Washington. You have some text, you run some dependency parser over it or some cheap approximation to it. You find the verb in the dependency parser. You pull out that verb string as the relation type and as arguments as the arguments to the relation, and you say that is the relation, just whatever the verb was, and that gives you a great diversity. Actually, in a way, this is a step in the right direction for the motivation I was giving at the beginning. This is incredibly broad coverage as is the web and keyword search. The issue is that I have no idea that attends may have anything to do with an affiliated relation. They're spelled differently, and they don't. There's no there's no spelling match, and so they're just different. I have no idea that they have anything to do with each other. So one thing we could do, yes. Okay. So this is exactly the direction that we're going to go in the body of the text. So the particular way to do that. So yes, thank you. Good. You're on the right track, or at least, well, I think it's the right track. So another solution that we actually worked in before we got to vectors was to do unsupervised clustering to discover these schemas. So you can find things like somebody authored a paper, they wrote a paper, published a paper, and we cluster these together, and any one of these implies the other. And so if I observe one and I'm asked about the other, I can still answer the question correctly. The issue is that I often see clusters that look like this one here. Like you're affiliated with the university, you attend a university, you're a professor at a university. You could sort of see how they got clustered together, but they don't all mean the same thing. One shouldn't always imply the other. So I think anytime we try to create some crisp schema, whether it's by hand or by some automated clustering, it's often arbitrary, hard to evaluate, a bit incomplete, has a lot of boundary cases. And the NLP community has been asking itself, well, where do these relation types really come from? Or even relation types, really simple ones like a cat is a mammal. We think we know what they mean, but there are incredibly strange boundary cases there as well, and so on. So in response to this, we've been working on this method that we call universal schema, and with apologies for the slightly hubristic name. All we really mean by universal is that we're going to operate on the union of all our inputs, of all input schemas. Right, if we're going to work with Freebase and also Wikipedia info boxes, rather than trying to map those onto a single schema to rule them all, we're just going to keep them both around, even though they're a bit different. Right? And that's because that mapping can be often really hard. Right? It's not the case that one relation type may entirely contain the other or the other way around. They may overlap like this. And furthermore, we're going to also use the original raw text, like OpenIE style, as another kind of schema. So all the raw textual expressions will be a very large schema of many different relation types, and we're going to keep those all around as well. But unlike OpenIE, we're going to learn some implicature among these entity relations and learn to fill in unobserved relations to understand when one thing might imply the other. Okay, so that was all a bit abstract. Let me just get a little bit more concrete by drawing a picture of how the model works. We're going to have a matrix with entity pairs in the rows, like Obama and US and Romedy and IBM. And in the columns, we're going to have entity types. And some of them will come from Freebase. Say about 10,000 of them may come from Freebase. Another 2,000 might come from some KBP task or from Wikipedia. And then many of them, say about maybe 50,000 of them or so, will come from little textual snippets that express relations. Yes?
If you're going to stick with Obama for the U.S.,
yes,
we request that you replace Stephen Harper.
You're right. That's very well justified. I absolutely should. Thank you. Yes, good. So apologies for the rest of the talk for having a bad example here. Sorry. Sorry, you said it the other way around. Actually, a good example. You're saying I should keep it the way it is. Is that what you're saying?
No.
I should. Okay. All right. Okay. Yes. Good. Yeah. Okay. That's what I should do. So I observe some of these intersections in the raw data that I'm given. Right? So like Freebase has the Obama head of U.S. In there. And in some text, I observed Obama, President of the United States, here. And so those I know already. If I'm asked, well, but is Obama the leader of the United States? Well, I didn't observe that, so I don't know that directly. But the idea is that through matrix completion, I should be able to fill that in and answer yes. So this is very much like the Netflix task, which I'm doing matrix completion to be able to reason about how all these things interact with each other. Before I get into the mechanics of that, let me just give a few examples of how this works coming from real data. When we actually run this at large scale on hundreds of thousands of documents, I can do things like observe that Stephen Forbes denounced George Bush and infer that he criticized George Bush. Just a kind of synonym relationship. Here's one that's a little bit more interesting. I observed that Volvo bought a stake in Scania, another car company, and I inferred it owns a percentage in Scania. It's kind of nice. My favorite example, because it shows the ability of the model to capture asymmetries, I observed that Kevin Boyle is a historian at Ohio State, and then infer that he's a professor at Ohio State. But when I observe that Freeman is a professor at Harvard, I don't necessarily infer that he's a historian. And note that the clustering model would not have been able to even represent this, right? Because everything that's in the same cluster has symmetric implicature. You can also apply this to entity types as well as relations. So you have individual entities on the rows, and I observe that Bill Gates is a person and a film subject and a chairman, and then I infer that he's a leader and an executive and so on. And so we reason about, not just 10 entity types or 100, but many thousands, plumbers and ballerinas and musical trios and all that. And, I infer that Peter Norton is a mogul from this evidence. And here I'm inferring a structured Freebase type from some textual evidence here. Okay. So in summary, we're embracing the diversity and ambiguity of the original inputs. We're thinking about entities and relations together. It's not an abstract relational mapping. This is an important. This is capturing something more rich than saying, if you observe this relation, then it always means this other relation is true also. It's interacting with the representation of the entity pairs at the same time. Because I might be tempted to say, if you acquire something, then you own it. But that's not true when you acquire a disease. And so it's important to reason about the entity. Okay, so here's where we are in the big picture. A little bit of motivation. Let's just talk a little bit about mechanics and learning. For those of you who know about matrix factorization, this is going to come as no surprises. We're going to get into some more rich things next. So to do this, let me first step all the way back to the beginning to give you the technical view and lead you in gently. So we have the text. We find a bunch of entity mentions. We do entity resolution on these mentions so we know which ones are referring to the same people. And we find places where we believe some relation is being expressed. And so it goes into some graph with entities as the nodes and relations as the edges. So this is like a knowledge graph. Doesn't do much good for us until we know really what the entity types are to be able to reason about them, or know what the relation types are to reason about them. Let's focus on entity types for now. The classic way to do this would be to build some classifier that for each entity type, I was going to say this in a different order. So because we're doing universal schema, we have not just the original schema that we started with, but we may import data from Freebase that has its own notion of entity types, and we also may find in the text a bunch of appositives, a certain grammatical structure that can be interpreted as an entity type. And so we have a very large number of them, which is what we mean by universal schema. And then the question is how to do prediction in this space. So the classic thing to do would be to build a classifier with a vector of, like a logistic regression classifier or something, with a vector of parameters for each different class. And these parameters sit in the space of raw observed features of the mentions that we're trying to classify. So lexical features of the words before and afterwards, and character suffixes and various things like that. And so there typically would be, say, a couple million parameters for each class. And that's getting to be a lot of parameters, right, for, say, 50,000 different entity types here. And maybe a little bit for scalability, not too much for scalability. More of the problems for overfitting, I think. So we're going to put the parameters in a much smaller dimensional space instead, maybe only 50 or 100 dimensions. This will be some latent space in which we'll learn neighborhood relations so that semantically similar entity types will be near each other. And we'll be able to map our entities into the space by embedding them in the same space and making predictions at the intersections by doing dot products of the learned vector embeddings for entities and the learned vector embeddings for entity types. And we can, so this is a matrix completion method that I imagine many of you know about. And we can train this very easily by picking some row, picking some positive instance for that row, picking an unobserved instance elsewhere in the same row, which we'll assume is negative, which may be a bad assumption, and just ask that the dot product score of the positive instance be larger than the negative one, and if it's not, get gradients from that. So we can, on a matrix, say that's 3 million by 50,000 trained on hundreds of thousands of documents on a single machine, we can fit these parameters in about a half an hour. So it's not so bad. We can apply the same thing to relation types. With many types and doing the matrix completion in the same way by learning embeddings for entity pairs and for the relation types. And so what does this mean? We have some knowledge graph. We can think of somewhat like Google's knowledge graph with entities for nodes and edges for relations. But unlike Google's knowledge graph, which has symbols sitting on the nodes and the edges, we now have vector embeddings that are capturing the semantics of what we're talking about. And I find this just really interesting, right? That it's a knowledge graph in which our semantics are represented by embeddings. And typically the thing you want to do with a knowledge graph is to reason about it, or do some logical reasoning. And there have been decades worth of work on logical reasoning with symbols, but now we're asking ourselves questions about, well, how do you do logical reasoning on vector embeddings instead? And that's exactly something we're going to get to here. Okay. Beforehand, I want to touch on two other things that help this model generalize and scale. And the first one has to do with going rowless. So let me explain what I mean by that. In this model, if at test time I observe some new entity pair, and I observe them maybe multiple times in the test set, and they appear in some textual context. So the text knows something about them, but because they didn't appear at training time, I didn't pre-learn a vector embedding for that entity pair. So I don't really know what to say about them. Whoops, I didn't mean to click that yet. So we're forced with doing a little bit of on-the-fly training at test time to try to estimate that row embedding for them. And it's just an engineering pain, and it's not so good for various reasons. So we've been working with methods in which we get rid of the row embedding entirely and estimate it on the fly by some aggregation function of the column vectors for which we do observe that data. So just like one simple way to think about this is that a not so bad estimate of a good row embedding is just the average of the column embeddings that were observed for that entity pair. And it turns out that a little bit more complicated aggregation functions like neural network attention mechanisms do even better than simple averages. And so this method reduces the number of parameters, so it helps us scale a bit better. It handles entity pairs that were unseen at training time. It also provides a more expressive kind of mixture model representation of the relation between an entity pair. Like think about Melinda Gates and Bill Gates. They have a complicated relationship. They're married, they're business partners in their foundation, and so on. And depending on the kind of question that I'm trying to answer about them, I might want to emphasize one aspect of the relation more than another. The old model just always took some sort of aggregate and represented their relation as the single aggregate. Now, my attention model can choose to look at different evidence differently depending on the nature of the question. And it increases accuracy, which I would have been happy with all of this and even a slight reduction in accuracy, but actually increases accuracy. That's nice. Okay. Next. Okay, so we just got rid of the row parameters. Let's get rid of the column parameters too. Okay, what do I mean by this? Let me motivate this. So here in these various columns, I have textual expressions that I observed at test time. Training time, sorry. At test time, I may observe some, English relational expression that I didn't see at training time, and so I'll have no idea what to say about it. But I would like to. So here's an example of this. It's like, sometimes there can be some big, hairy, huge textual expression that really does have a semantic meaning, right? Like that Gates lives near Seattle. But there's no way I'm going to see exactly the string of text multiple times. It has too many specifics in it. I would like to be able to generalize over this. I would like to get a vector embedding for that. So what we've been doing is getting rid of, let's see, how do I do this? Getting rid of those column parameters, having instead parameters that are embeddings for the individual words in these relational expressions, and having some pattern encoder that stitches together the semantics of these all together to produce column embeddings for these relation expressions on the fly, including for these really long relation expressions that I see only once. So that, say, when I observe this relation expression, I get an embedding for it that can allow me to infer that some other columns are true as well, and then make predictions about this evidence that I saw only once. And as you might have guessed, the pattern encoder we're using an LSTM that basically consumes the sequence of word vectors in order to compose them together into some semantic vector that captures the nature of the relation. Okay, so this handful of relational text unseen at training time. It enables multilingual cross-training. I forgot if I took out the slides for this, so we'll see in a minute. And it also increases accuracy. I'll skip over this. So, we jumped from 35 to 41% accuracy. And here's some examples of the kinds of relational text that we can interpret. Right? Things like, took a pay cut for the $80 a week job as an associate director, and we correctly interpret this as somebody having this job title. Right? Or thinks that she can stay in office after a jury found her guilty of misdemeanor theft. Are interpreting that as well. Yes, David. Still keep what? Sorry?
Do you go entirely columnist, or do you still keep instead of?
Okay. Thank you. I'm glad that you asked that, and maybe that means I should not have skipped over something quite so quickly. Let's see here. Oops. Oh gosh. So one thing is that we will. Oh gosh, I skipped it again. I'll just say it. We do keep free parameters for each one of the relation types that are in a structured knowledge base. So it's only the text over which we're learning these at the time. And so, so at test time, we might consume the sequence of textual things, put it through a bidirectional LSTM, have some max pooling to get a single vector to represent the whole thing. And then we can do things like compare that single vector for this text with the learned free parameter embedding for the structured database relation spouse. Does that answer your question?
Yeah.
Okay, good. Yeah.
So to some extent, is this mapping doing what we were doing originally, which is making longer text to be able to map it back to relations?
Yes. Yep. Exactly. We've also done work in which we have no database at all, only the text, and yet you can still see co-occurrences of where the same text is applied to the same two entities, and learning to generalize from just the text alone. And I find that super intriguing. Okay. I think, how am I doing for time? I think for the sake of time, I'm going to skip some multilingual stuff and now just talk about multi-hop reasoning. Okay, sorry? Am I? Okay, yeah. So actually, when should I end? It doesn't, okay. We could be here for the next 3 hours. Great, okay. Okay, so let's say that somebody asked me about the nature of the relationship between Melinda and Seattle. I didn't observe any sentence in which they co-occurred at all. But I'd still like to make some prediction. Well, I do have some evidence, right? Melinda is married to Bill, chairman at Microsoft, who has its headquarters in Seattle, and maybe I should be able to do that to infer that with some probability that Melinda lives in Seattle. And there's been work in numerous corners, including some work by a student of William Cohen at CMU about 4 years ago that learned symbolic rules to exactly capture this kind of reasoning, a rule just like this. The issue there is that, well, but what if you observe CEO instead of chairman, right? Or COO, or maybe child instead of spouse? You'd still like to be able to make this prediction, but these symbolic rules, as they always are just incredibly brittle and give you no answer if you've only learned the top one. But note that we have not just symbols, but vector embeddings on each one of these edges that can help us generalize. So, in a 2015 ACL paper, we have a system that uses a deep recursive neural network to consume the vector embeddings in order along the path from one endpoint to the other, at each stage composing them together and outputting a vector that the system believes represents the nature of the relation between the two endpoints so far. And by the time it's traversed this entire path, it indeed outputs a vector that's very close to the vector embedding for the lives-in relation. So this is doing, some sort of logical, something like logical reasoning on top of vectors instead of symbols. And all of the things that were previously we would have created a list of rules, that information is somehow just sitting in the parameters of this network. Okay. So, on a moderate amount of data, we ran this task. And here are a few examples of paths that we found to be predictive. Oh, yes, thank you. Yes. Great question. Yes, okay, I didn't say that at all. Okay, I'm so glad you asked. We train by, so there are two storylines I can tell. One way is that we'll find a cycle, and then we'll remove one edge from that cycle, and then follow the rest of the path, and ask that the neural network, when following that path, says yes to the relation type that we just removed.
How would you have something that's highly correlated, but that isn't really? So as an example, Bill is a friend of Steve.
Yes.
And Steve is a CEO of Microsoft.
Yeah.
And I'm envisioning, let's say we're in a world
yeah.
where CEOs and chairmen can be friends with each other.
Yeah.
But that shouldn't mean that Bill is a chairman of Microsoft, which you'll see on the diagram.
Oh, sorry. I see that we're afraid that we would learn that anyone who has a friend who's a CEO, that would imply chairman. Okay. Yeah. Good. Okay. So, I don't have a particular, that's a great question. I don't have a particularly magical answer for you other than to say this would just be seen by the system as noisy training data. If the correlation were high enough, then it would say yes to this. And I think the natural data, I know you weren't picking this as a great example of real correlation, but I guess what I imagine is that, yes, we would see paths like this, and we might actually see it more than once, but we wouldn't see it often enough. They would actually be trained to say yes there. Something that since you're asking such a good question now, I'll sort of a preview of something that I'll mention briefly at the end, which is we have an iClear paper from a couple of years ago that learns semantics not just in terms of vector embeddings that represent points in space, but represent instead Gaussian regions in space. So it's like the embedding is both a mean and a variance. And work that we're doing now actually take the LSTM, consumes some relation expression, and produces not a vector point in space, but a Gaussian region in space to expresses some degree of the breadth of the semantics or some uncertainty, and we're thinking that this may help exactly some of the issues you're asking about. Yeah.
Training some kind of
yes.
And for other point of view, it's recursive network.
Yeah.
Which is why it means something like. So this is recursive mean infinity.
That's right. So the loop could be an arbitrary length that we're not fixing in advance.
Pseudo-infinite, something like training. Like recursive, it's infinite.
Yes.
If which is new, it means you send the same information, something like that.
Oh, we do.
Yeah.
Well, so we don't travel through the same loop repeated times. Let's see here. I mean, another way to describe the mechanics about how we gather training data, which is maybe a little different than what you're describing. So, we'll pick two entities that have a relation. We'll do random graph walks to find, say, 1,000 paths between this pair, and some of those paths are actually meaningful, and some are not. And we'd like to especially train in the meaningful one. You can think about this almost like some EM problem. We don't know what's meaningful in advance, but hopefully we can estimate it and bootstrap ourselves. And so we'll actually score all 1,000 paths, pick the path that we think is most indicative of what we want to be able to say yes to, and focus our training on that one. Okay. Yes?
Instead of using non-symmetric...
sorry, what method?
Using non-symmetrical similarities for some relationships, like Microsoft Seattle.
Yes.
The relationship is not symmetric.
Yes.
Microsoft isn't Seattle, but Seattle is not a Microsoft.
Right. Yes. Great question. And I've also, because again, I was a bit unclear, we actually have separate parameters for traveling an edge in one direction versus the other. The other, just now that you're talking about symmetry, that I want another thing that we really like about the Gaussians is when you're trying to measure, say, distance between two vectors with a dot product, it's symmetric. But with Gaussian embeddings, you can talk about KL divergence of the overlap, and it's non-symmetric, which also has nice properties. Yeah. Okay. So we're trying to predict that this book A, the original language in which that book was written was language B. And the model finds that one path that provides some evidence is, well, what's another book that was the previous one in the series of books, and what was the author of that book, and what was that author's nationality, and what's another person with the same nationality, and what language does that person speak? No, not bad. I don't know. Right? And here are some other examples, right? So I know that the book takes place in, so here's a piece of text, a place where people have this nationality, takes place in this nationality, and here's a person with that nationality in a language that person speaks. So anyway. Okay, so we've also more recently been adding information about entity types as well in order to address this problem, which is we could look at this JFK airport located in New York City, located in New York State, and we observe this airport serves the state of New York in our database, and then write a rule that looks like this. And it seems like a good rule until we realize that also would say yes to Yankee Stadium being an airport that serves a place. And so we've just not captured entity types here. So that's what we would like to do. So we capture entity types and modify our recurrent neural network to incorporate them both, and we do better, as shown here. So this work from CMU that I was mentioning earlier that uses symbolic rules gets a number like this. The work that I've described so far that uses recurrent neural networks, and actually I didn't say this in great detail, but actually the original work from the 2015 ACL paper has a separate RNN for each one of the 42 different relation types that we were trying to predict in our relation test set. And that's pretty sad for numerous reasons. One is it's a lot of training to do. The other is that we can only predict 42 different types, and I'd like to be able to do it more broadly. So in later work, we actually made a single larger capacity RNN to predict across all types. And again, I would have been happy if the accuracy fell, just because it was more convenient, but accuracy actually rose. So it's like learning to do, it's like some multitask learning across predicting different relation types. And then throw in the entity types as well, we do even better still. And I'm like this I don't really consider so usable, but this is a quite usable number. We were very pleased to see this. Okay, so lastly, I'm actually almost done. So I want to step back and think about the knowledge representation that we have here. And broadly speaking, something that's really been on my mind is this big, age-old, big AI question about, well, knowledge representation, and how should we do this, and what is a style of knowledge representation that will allow us to generalize and also reason, and this is getting close to something that I would advocate for strongly. And I've actually been having conversations with my friends at Google about, well, what should the next version of their knowledge graph look like, and have been advocating for things like this and getting some interest from them. So when we account for the fact that we're rowless, what that means in a way is that we don't have a single vector summary for the entirety of the relationship between Bill and Andy here, but there are many edges. And in fact, you could think there are as many edges between each entity pair as there were sentences in the original raw corpus that included those two entity pairs. So I don't know if some of you are familiar with the Facebook baby data set, in which there are a number of sentences, and there's an embedding for each sentence, and the knowledge representation is basically just a big list of all of the raw sentences with embeddings for each. This is now a bit like that, in that there will be some representation for every sentence in the corpus. We're reasoning in a way that's very close to the original raw text. A difference in how I think this should be tackled than how folks, like the Facebook folks, reason is that I believe in entity resolution, and so we do that, and we form nodes in a graph and really pull them together. So my point here is that we built a very large graph here, and that answering questions often consists of finding paths in this graph. And so lately we've been thinking about using reinforcement learning to guide the search for a proof to the answer of some question in this very large graph. This is some ongoing work that we're doing now. So this is basically a replacement for the random graph walking that we described earlier, and our what's the word? Headroom investigation shows that there's a lot of room to find better paths here by searching for them more intelligently. All right, let's see here. So I mentioned briefly these Gaussian embeddings. This shows an example, and this is actually not just drawn artistically from out of my head. This is actually a projection of embeddings actually learned from Wikipedia. And so it's learning Gaussian-shaped embeddings for these concepts, and you really do find that broad general concepts like person have large variance. More narrow concepts like musical composer are smaller and contained inside of person. Cross-cutting concepts like famous can be seen here. And yeah, Johann Sebastian Bach sits right at the intersection, right where you'd like to see him. It's pretty cool. So yeah, now these were learned in which they were free parameters for means and variances with each word. Now we're trying to work on compositional models that can take a sequence of words and have the LSTM output not just a vector, but output a Gaussian instead. All right, I think I'm not going to talk about this last thing because I'm actually going to mention it a bit tomorrow, and it's pretty disconnected from what I've said so far, and that will leave us more time for discussion and questions now. I'll close with this. Thank you very much. Yes?
General question. You haven't said much about the queries, and I'm wondering, is there much information there?
Yes. Yeah, okay. So in the evaluations that we've done so far, the queries have been pretty sadly simple, right? They're a very structured. We're basically just asking, here's an entity pair, what's the nature of the relationship between them? Or here's an entity and a relation, what are the other entities on the other side of this? And there's no textual interpretation of the question. The question already comes to us in structured, packaged form. The work that I just skipped actually talks about how to interpret a more complicated question. And if there's high demand, and people would like to hear briefly about that now, I could go back and talk about that. A way that I've been thinking about this lately is that if you a question can often be interpreted as some subgraph with some missing hole, and then it becomes a matter of graph matching of this little subgraph onto the massive knowledge base, and how to do some alignment of the question with what you know so far and see where your blank sits, and then use that to answer the question. But am I answering in the direction that you were asking about? Okay, yeah. Yes?
Have you thought at all about negation?
Oh gosh, that's a great question. So the answer is we've been avoiding it because it seems so hard. Do you have any advice for us? I don't know.
An implication that you already have destruction and negation, and you've got horn clauses next. So
yeah, and right. We've been very eager to, just for the sake of our interest in having more complicated machine learning models, to build reasoning that would be over more than just some linear chain of connections, something that would have loops and a whole little subgraph to it, and little appendages sticking off in different directions. And we've had a surprisingly hard time finding real-world cases where something more than the linear chain is really necessary. And maybe this is just our complete lack of imagination or our lack of background knowledge of the decades worth of symbolic reasoning work that's been done. But so that's one data point. And yeah, the other one, I do think things get much harder when you think about negation, right? And One thing I wonder about is whether the Gaussians will help there also, because then we can do things like say, well, here I have this region, and then things outside the region are just false. Or, but yeah, if you do have suggestions for me, I would love to talk with you one-on-one after. Yeah, Rich.
So, maybe related to this is you were talking about the training, and whether there's ever something like a negative example.
Mm-hmm.
Have you ever had cases where you think of, and that's a way to build up your system a lot more?
Yeah, absolutely. Right.
Either explicit or implicitly. Use of negative examples.
Sure. So in the original universal schema without the paths, we do sample these unobserved cells and treat them as if they were negative. And that does get us into trouble sometimes, obviously. And we just haven't been working with data sets so far in which there are explicit negatives. If we had explicit negatives, they would fall cleanly into the objective function and we'd be able to use them, and I think they would really help a lot. One of my first-year students is now starting work on active learning for matrix factorization, matrix completion, and so we could really then solicit from humans particular answers, and we could ask about negatives as well, and I think that would be...
Because I was thinking in the paths, when they're following multiple paths.
Right.
And then some of those paths may be good paths, and some of them are...
Yeah, okay, great. Let me say some more things. So not only wrong, like, you took this path and you might have predicted this relation, but that's just objectively false, and so you should train against that. The other is that you could find paths that really are not meaningful paths. Like I could have gone from Melinda to her alma mater, to the chancellor of the alma mater, to the chancellor's daughter, to where the chancellor's daughter got married, and that just got married in Seattle, but that doesn't really mean anything. The other is that, and this maybe relates to reasoning about negations a bit as well. Okay. So right now, in the face of many possible paths, if I'm asking a question, I do random walk to sample 1,000 paths, I evaluate all of them, and I find the one that most strongly is trying to say yes to the question, and if it says yes above threshold, I say yes. And that can get me into trouble because I did not explicitly reason about negative evidence. If somebody asked me, do Bill and Melinda Gates hate each other? Amongst all of my massive document set, I could find a sentence describing an argument that they had. And maybe that's from that evidence alone, I would conclude that they hate each other. But then I just ignored all the evidence about how they're married and they have children and all these other things. That seems wrong. So these are all current areas of exploration. Yeah, Raquel.
So maybe the mechanisms here seem relatively static.
Yes.
Change over time.
Yes. Oh gosh. Yes. Okay. So for some of you, maybe you didn't hear it back. So we've not modeled time at all here, and how relations, change over time. Obama and U.S. being the prime sad example. So I don't have much smart to say about this. Let's see. Gerhard Weikum, who is a database researcher in Germany, who's done some thinking about knowledge bases, has a little bit of here. My current notion is that, especially in this world in which we have an edge per sentence, that each of those sentences now has a timestamp, and that I could then incorporate into this path kind of reasoning. Well, I'd only like to follow paths with certain timestamp recencies, or what I would like to avoid doing is having to do sort of non-monotonic reasoning, like to say, well, this was true at one time, but then but now I think it's no longer true, and so I have to somehow edit my knowledge base. And this is consistent with, broadly speaking, with the view that I described in the very beginning about the epistemological knowledge bases, where the only thing you're allowed to enter is the evidence. So there's, in a way, you could consider that we're not storing a lot of the conclusions of inference, is how I think I would solve this. I would just store the evidence and then try to build really fast methods for traversing these paths. And so I'd never have to take away any former conclusions, because I would never store any conclusions. How to incorporate time in useful ways into these path traversals, I think, is an interesting question for which I don't have preliminary answers. Yeah, thank you. Anything else? This has been a great set of questions. Thank you. Yes?
The reinforcement learning technique for trying to go over paths. So it sounds like you're trying to find
Yeah.
So I assume what you're trying to come up with is policies at each edge that will, non-deterministic policies at each edge that will.
Yeah, so yes, I think given the Bill and Melinda Gates arguing and maybe hating each other but not example, that is a case where we really should be finding multiple paths. And our work so far, we're putting that aside and saying, no, actually, I would be happy to find one path that's a good proof, but just let me find a good one. Explore to find a good one in the midst of this massive graph. And we're setting up reinforcement learning such that, right, you start exploring from arg1 of the binary relation, and you get reward when you arrive at arg2 with a vector representation of the path that gives a correct prediction. And then trying to pass that reward back through paths that we explore. Does that make sense, or did you have a follow-up question? Okay, there's a lot to be done there as well. If you have particular thoughts about that, I would love to talk about this. This is work in progress right now, and
Is that overkill? Why not do something like 3 stars? Something like that? Is it perhaps too big? Or?
Oh, I see. That's that could be the case actually, right? I have to be careful not to overkill with these methods. Let's see here. What would that representation look like? We'll see. So how would you characterize something for which A star is not sufficient, but reinforcement learning is the right answer?
Need for non-determinism.
Yeah.
It's coming up with it.
Yeah. Right. Yeah, I think that's right. Yeah. Yes.
I might not understand the actual relationship score exactly, but how do you guys deal with abstractions?
You mean things like a dog is a mammal is an animal? Or?
Something like that. You said earlier that you store each relationship separately. Then abstract relationship on top here.
Okay, yeah, so, yeah.
Earlier, like for example, I have one set of negation, but I'm learning all other set of methods.
Right.
But if I can hold down top of the abstraction.
Right, yeah. Yeah. We haven't thought at all about meta-reasoning, right? Like reasoning about the schema itself. Like you could imagine having, multi-hop reasoning that's not passing through entities, but passing through nodes of the schema. And we're not doing that at all right now. So the extent of our meta-reasoning is just that certain symbols for relation types fall near each other in embedded space, or have overlapping Gaussians, or something like that. And we are currently doing work, I mentioned common sense here. So running universal schema or methods like this on not proper nouns but common nouns, to me is an instance of common sense. And we are currently doing some work on relations among common nouns, where we also are learning at the same time about ISA relations and about non-ISA relations at the same time. And actually, instead of the Gaussian embeddings, we're using the order embeddings paper that comes from here, right? Yes.
In the talk, how do you actually decide which relations you are learning? You said that clustering didn't work, so do you manually select the set of relations that you are learning? And if you see a new relation in the set that you haven't seen in the training set, do you add this to the set of relations?
Right, I'm glad you asked. We're learning about all relations all at once by learning embeddings for, say, all 50,000 columns that were there, and by having the compositional LSTM on new textual expressions, able to build a representation for some relation string that we never saw until test time.
So you have determined the set of relations before that?
Well, maybe this is the definition. So maybe by set of relations, you mean like the semantic space of relations. And I guess there I say it's the embedded space that becomes that semantic space. And we're relying on neighborhoods in this embedded space capturing the semantics that are necessary. And that's also, I think, an open question about the degree to which we can be successful there. And we have other, actually, more core machine learning work, learning embeddings in some different way that I can't get into right now, but that may expand our optimism about the degree to really represent very diverse semantics in an embedded space. Yeah.
Comment on the star note.
Yes.
I think if we
Yeah.
If we're busy with without samples.
So I think he is very powerful.
Curiosity, right. Yeah, I agree. And I mean, I understand the reinforcement learning is a black box procedure, how I may have a chance to learn that. If I were to hand design such a heuristic, I don't know how I would do it. Yeah. All right. Okay, maybe last one.
Graph representation, do the edges have the same weight? Or is the weight, or can you encode information in the weight of an edge? Say like time decay or something like that.
Let's see here. I don't think about our edges as having weights. There's an embedding on each edge, but maybe I'm misunderstanding your question.
Bill Gates lives in Seattle.
Yes.
There is a link between the two. That link was observed at a certain time.
Yes.
And as time progresses, the link is weaker and weaker.
Yeah. Oh, so we're not doing that now, certainly. I mean, this is back to Raquel's question about changes over time. We're not reasoning about time at all. We're also not reasoning currently about the reliability of different sources. No. We could still have some uncertainty, represent uncertainty about whether Melinda lives in Seattle, and that would be based on how close is the vector embedding that is the result of the RNN to the symbol lives in. And it could be, right on top or close enough, but not very close, and so on. Yeah. All right. Thank you so much. These have been great questions.
Thanks.